All right, last objective focused on independence. So here are what independent events are. Independent events are two events that if you know one has occurred or not, it does not change the probability of the other event. So notice here, this is a conditional probability. This is saying the probability of B given A, given A. That means A has already occurred. Well, notice that the probability of B given A is the same thing as the probability of B. What this means is it doesn't matter that A already occurred. A has no influence on B. The probability of B stays the same. This is an important test to see if your two events are independent, and we will use this test on our future examples. Okay? All right. So here we go. Example 3, are more males or females left-handed? Is there a relationship between gender and handedness? To find out, we chose an SRS of 100 Australian high school students who completed a survey. The two-way table summarizes the relationship between the gender and dominant hand of each student. So there's our table. Suppose we choose one of the students in the sample at random. Are the events male and left-handed independent? Let's let M stand for male. Let's let L stand for left-handed. Here are your males. Here are your left-handeds. So what I want you to do is I want you to think about which one is the explanatory, which one is the response. What is the variable that we don't like we set at the beginning, and what are we trying to measure? Well, I think that gender is the explanatory, and I think we're really trying to find the probability of being a certain hand. So this is my response. So what this means is the conditional probability I want to find is the probability of being left-handed given that I'm a male. If that's the case, then I need to test this against versus what's the probability of just being left-handed? Because if I look at these two probabilities, in both cases, I'm measuring left-handedness. But in one, I'm trying to see if being a male influences or not. Okay, so let's do the conditional probability first. So this is what I'm given. Let me do it in red. So I'm given that I am a male. So again, that means that I'm only looking at the males for this one. And that would be I'm only looking at 46. And of those 46, how many of them are also left-handed? 7. 7 out of 46. And I'll do 7 divided by 46. And that's 0.152. 0.152. So now I'm going to look at what is just the generic probability of being left-handed. No more conditional probability involved. All right, let me use some other than green. Green's tough orange. Okay. Well, now look at all your left-handed people. All your left-handed people are 10. And now, because there's no condition, we actually use the total. And the total is 100. And 10 divided by 100 is 0.1 even. And are these two probabilities the same or are they different? They are different. And because they're different, male had an effect on left-handedness. It actually increased the probability of being left-handed from 0.1 to 0.15. So these two events are not independent. They're not independent. So we will say, because the probability of L given M does not equal the probability of L, these events are not independent. So finally, when it says not equals, it's not independent. So it matches, right? Finally matches, not backwards. There we go. Okay. So again, to me, the most important thing is this at the beginning. But it doesn't really matter. If you would have said, let's find the probability of M given L, then just make sure you find the probability of M and compare those. Okay? So it really doesn't matter the order of your conditional, just as long as you find the probability of, what you're trying to find the probability of as well. But again, this probability, M given L, is not the same as L given M. M given L is not the same as L given M. The order matters. All right, so best of luck with this independence I'm here to help if you need me.